Hey everyone, welcome back. It's the second session about reading proof arguments and zero knowledge. And today we're going to continue where we left. I think we left approximately like at this stage, univariate Lagrange interpolation. And we're going to continue quickly. Like we're going to do a cool stream about it. This was the note we took last time, but I think we're gonna start new one today. We're just gonna start new ones. And yeah. So I also did like notes here, and I made this note into my knowledge base afterwards. Like if I type like Freiwald algorithm. So this is on Obsidian. You can find it on my website, matteo.dev, Matteo with the a.dev like this, and you don't see it on the screen, but there is a page with notes. I click there and you have my notes. Because I think I can't post links for now on YouTube. I'm just thinking. So yeah, let's continue our learning session. I think it was super cool the first time, so I want to continue. Session 2. Let's do the second session. Okay. So let's start. I think my setup is a bit better than last time. I still need to not write where my camera is for the stream, but I think it's alright. Okay. So I think we read that last time, but we can refresh ourselves. So read-Solomon encoding is of a vector A in the field described in section 2.3. Interpret A as coefficients of a univariate polynomial P of A of degree n minus 1. So they interpret it as coefficients, right? So what the encoding does, just as a reminder, it's like do this. I think it's written here, but it creates a polynomial P of A such that every coefficient in the vector is every number in the vector, let's say, I don't find the right word, is a coefficient in the polynomial P of X, which is equal to the sum of every coefficient time random x to the power I minus 1. So it creates a variable, it creates a polynomial of degree n minus 1, because I is n. So that's this. Sorry, it's alright. So there is our way to interpret A as the description of a univariate polynomial QA of degree minus 1. The most natural such alternative would be to view A1, like the vector A, as evaluations of QA over some canonical set of inputs, let's say 0, 1, until n minus 1. So just to come back on this, what they're meaning is, instead of create, like if you have your vector A, which is the encoding, so the vector A is the encoding AI AN, I mean A1 AN, and instead of putting it like if you remember, P of X was equal something like A1 X 0 plus plus AN X n minus 1. So that was the polynomial we just talked about last time, to interpret the encoding. But we can also, so they're saying you can also just do something where basically we'll have a set of inputs. Q of X will be equal to, we don't know what, but the set of how can I describe it? Like if you will have this set of input like I don't know, which will be like they're saying 1, n. I mean, it starts at 0, but yeah. And you will do p of 0 equal a0, p of 1 equal a1, p of n equal an. That's what they're saying. N minus 1, yeah. N minus 1, a minus 1, yeah. N minus 1, I don't know. A1, yeah. A1, A2. I'm sorry, I'm not very precise today. I need to get into right form. Thank you, Léo. Regarde Valorant ce soir au lieu d'être sur le chat. So it's what we saw last time. That's what they're saying here. As we now explain, for any list n, input output. Okay, for any n pairs of input output, there is a unique univariate polynomial of degree n minus 1 consistent with those pairs. The process of defining this polynomial Q of A is called Lagrange interpolation for univariate polynomial. Merci Léo. So basically finding this polynomial that we don't know is Lagrange interpolation. So yeah, I'm very French now. Interpolation. So let's write this lemma quickly, maybe, or read it at least. Let P be a prime larger than n, and Fp the field of the modulo integer P. Okay. For any vector A equal a1 until an in the field, I think it's like, I don't exactly remember how to say this, but it's like f times f, and this is like I'm really bad today. It's like n time, if I remember. This is the field we're talking about, because the vector is like, you know, multidimensional. C'est quel niveau de maths? C'est, je sais pas. C'est juste très précis. C'est des maths liés à la cryptographie et au zero knowledge en règle générale. J'avoue que j'ai pas fait de maths à l'université, donc je pourrais pas te dire. So let's continue. Okay. There is a unique univariate polynomial Q of A at a degree at most n minus 1 such that Q of I equal A of I plus 1 for E. Okay. So that's what I was saying. The lemma is basically saying that there is always a polynomial that does this thing. There is always a polynomial that does this. Oui, j'ai fait 6 mois d'apprentissage en solo, ou plus même, pour comprendre ces maths-là. Justement, je continue d'apprendre là, c'est ce que je fais en live. Okay. So, let's continue. So, the lemma says that Lagrange interpolation will always work in a prime field for any vector. Okay, the proof, I think we can, I think we can skip the proof here because I don't like proofs. This is the kind of black box I agree to take, the proofs of things in general. I think it's very formal. Within expression. We give an explicit expression for the polynomial QA with the behavior claim in expression 2.2. To do so, we introduce the notion of Lagrange Bayes polynomial. Maybe we need to read that still. Okay. Comment tu tombes sur le stream d'ailleurs? Ça m'étonne d'avoir des Français. À part Léo. Lagrange Bayes polynomial. For each I in the inputs, define the following univariate polynomial. I don't know how we say that over FP. Et bah, bienvenue. J'ai vraiment lancé mon stream il y a 10 minutes, donc c'était vraiment le destin. Mais en gros, c'est des maths pour faire de la cryptographie. Et le but, c'est d'arriver à comprendre mathématiquement ce que c'est qu'une zero knowledge proof, qui permet de faire des trucs très cool, de prouver des choses et tout. Mais ça, c'est plutôt de l'abstract algebra, comme disent les Anglais. Sorry for my French speaking. Okay, 1 second. First, parce que j'ai plutôt déjà le truc il est en anglais, donc c'est plus simple de lire, d'aussi parler en anglais, et aussi parce que j'ai plutôt des followers anglais parce que je poste ça sur Twitter et j'ai plutôt des followers anglais normalement, et aussi je poste sur YouTube, et aussi juste en fait tout le milieu parle en anglais, donc je fais ça en anglais. Ok. Okay. So, okay. X minus k. So the polynomial would be something like just, I don't know how to write it, but zero. Okay. So this will be the polynomial. So it's straightforward to check that the polynomial has degree at most n minus 1. Yeah, okay. Since the product on the right hand is equaling that n minus 1 term, each of which is a polynomial in x of degree 1. Just trying to check if it's the... Whoa. Is it the proof or... Okay, it starts to get very specific. Okay. So this is the polynomial, the Lagrange Bayes polynomial. So my writing is terrible. Let's say like this, it works. Okay. I minus k, k equals 0, 1, n minus 1, and k different I, not I. Okay, so it's interesting. Okay. Yeah, k different y. You can easily make the link. Firstly, I forgot to do that because it will make 0. It will be 0. So I'm a bit distracted. I will start to focus again to work. So I do this. So this is Lagrange basis polynomial. Lagrange basis polynomial. It's straightforward that to check that. Okay, let's just. I want to. How to pronounce. Yeah. Delta. Ah, okay, it's delta. I'm not Greek, okay? I don't know the letters. Delta I of x. Okay. By the way, it's delta I. Yeah, of course. So as degree at most n minus 1, since the product on the right hand has n minus 1 term, which each of which is a polynomial in x. Wait. Of equation 2.3. Okay, I'm missing something here. Since the product. Thank you, it doesn't work. I'm missing something, but I will just let it go for now so I can continue. This polynomial has a degree at most n minus 1. Moreover, it can be checked that delta of I maps I to 1 and maps all over points in 0 to 0. Wait. There is something I don't understand right now. Not, however, that delta I of R does not equal 0 for points that are not, okay. But let's say, okay, let's try, like, delta of 4 modulo, okay, let's do, so n will be, that's the, okay, what's I here? Okay, that's the inputs. Inputs will be something like, let's try to understand it by doing it. The inputs, maybe I should do big I, we're doing math, not coding, equal 0, 1, n minus 1, let's say n equals 10, 13 is prime, right? Yeah, I'm almost sure, but yes. Phi equal 13. I just don't want to mess my own calculation for a stupid mistake like this. So let's take I equal 3, right? And then we do delta of 3 equals, oh, I'm gonna have to do 10. Okay, let's do 4. So it will be something like x minus 0 divided by k minus I minus k. So I is 3. So it's 3 minus 0. 3 minus 0. And it's like time. Ah, yeah, you can just compact it, right? Yeah. I'm just seeing this part now, and I think it makes more sense to write it that way. So I will do it that way. It will be like x minus 0, x minus 1, x minus 2, x minus 3, right? And then, because it's 4, k is until minus 1, yeah. Okay, so then it's 3 minus 0, 3 minus 1, 3 minus 2, 3 minus 3, yeah, there is not 3 minus 3 because, but we just exactly take n equal 4 here. There's something I don't understand. Okay, n equals 4. Okay, yeah, okay. So it's still working, right? Because n equals 4. Oh yeah, n minus 1. 1, 2, 3, 4. Yeah, my bad. Okay, they are actually doing exactly what I'm doing right now, which is fun, but I will do it myself. So it's gonna be, if we take, okay, so it's gonna be x times x minus 1 times x minus 2. So it's gonna be, yeah, they're saying it's gonna be 6, yeah. Yeah, the opposite of 6. Okay, in the field. Yeah, I understand now. Okay. So if you didn't understand, yeah, in modular mathematics, to divide you, I mean, I think in normal mathematics as well, but you can just do, so it will be, let me finish my thing. 3 minus 2 is 1, 2, so it's 3 times 2, so it's 6, and you divide by 6, so you actually multiply by the inverse of 6, which is 6 to the power of minus 1, times the thing you want to multiply it by, and you do this mod p. Okay, so this works, and it's pretty normal that you can see here that it's like the maximum degree will be like n minus 1, because you do there's like x times x times x, which is 3. We understand correctly. Okay, it's making sense. So the delta is the Lagrange basis polynomial, which looks something like this. So if you want to express Q of A in terms of Lagrange basis polynomial, okay, expressing K. Okay, now we're gonna do expressing Q of A of Lagrange basis polynomial. Okay. Recall that we wish to identify a polynomial Q of A of degree n-1 such that Q of A of I equals AI plus 1. Oh yeah, okay. I plus 1. Sorry, not AI plus 1. A of I plus 1. A of I plus 1. for every input. We define such polynomial QFA in the term of Lagrange basis polynomial in the term of Lagrange basis polynomial. Whoa, sorry guys. Okay. Okay, I think I just skipped this part and it seems important. Moreover, it can be checked that delta of I maps I to 1 and maps all our points in the input to 0. Okay, let's try. Sorry. Delta of delta 3 of 2 equals 6 minus 1 times 2 times 2 minus 1 times 2 minus 2, which is 0. Yeah, because this is 0, 0. So this is this times 0, so it's like 0. Okay, so this is 0, okay, for sure. I agree with you, man. And then S3 of 3 will be equal to 6 minus 1 times 3 times 3 minus 1 times 3 minus 2. So it will be 1. This will be, yeah, and mod p, right? So okay, it will be 2. So it's gonna be 6 times, yeah, we don't even need to, it's equal 1. I mean, it's equal to the identity, which is 1. The multiplicative identity, which is 1. Oh yeah, sorry, let me do, I did this, just wrote 6 minus 1, I did 6 minus 1 times 3, which is x, this is 2, this is 1, and then it goes like everything like this is, it's a 6, so it's 6 times the inverse of, multiplicative inverse of 6, which is 1. So you guys are right. So what are they saying about this? Sorry. In this way, okay. In this way, delta of I acts as an indicator function for an input I. In that, it maps I to 1 and kills all the other inputs in the input. So delta of I is referred to the I guess Lagrange basis polynomial. So the basis polynomial, so just to write it somewhere, Lagrange basis polynomial is a polynomial that for a set of input, I mean, it's a polynomial, how to explain it? It's a polynomial that helps to detect one input and killing the others, kinda. If I understand correctly, it's the idea. Okay. So we can use it to describe QA of x as QA of x equal the sum. Okay, wait. Ah. Okay. I'm gonna write it and then try to understand it, but it's not exactly this. It's like this? No, it's definitely not like this. Okay, I understand now. Okay. J equals 0. J plus 1. I'm so bad at writing stuff. J of x. So it's the sum. It's the sum of a of j plus 1 times the basis polynomial, the Lagrange basis polynomial of this input, kind of. Yeah. So it means that if I take an x which is not this input, it's so smart. I think I start to understand. The idea is, let's say I do q of a of 2. Every polynomial, since the polynomial will be actually equal to just a of 2, a of 3, yeah, a of 3, a of 3 times s2 of 2, because this is 1, right? And this is, and every other, like for example s delta of 3 will be equal to 0 because it's 2. So the polynomial will be like only giving the right aj plus 1 for the right x, kind of. If you understand what I mean. It's so smart. It's so smart. I don't know if I was very clear, so I will try to explain it again. This is gonna give 1 only if x is equal to j, right? We know that. If x is equal to 3, then we get 1 here. So, and if it's equal to 2, then it's not equal. So if j is equal to x, it will be 1. And if we multiply, and so for every time it's not, x is not equal to j, it will be 0. So basically this input will be like killed, because it will be this input times 0. And the only one that will get 1, so that we will get the right a of j, is when x will be equal to j. So we will get only the right a for the right x. Okay, I hope it makes sense. Okay, let's read it. It will get clearer than my dumb explanation. Indeed, for any I in the inputs, every term in the sum on the right hand side of the equation, other than the if, evaluates to 0. So that's what I was saying. Because a sj of I equals 0 for j different of I. Meanwhile, the if I term evaluates to a of j, ai plus 1, yeah, times this, which will equal to 1, equal ai plus 1 as desired. Yeah, super cool. Okay, this is how we can build the equation. Yeah, it's very cool actually. Very, very smart. I like it. So establishing uniqueness. The fact that Q of A defined in 2.8 is unique polynomial of degree at most n minus 1 satisfies equation 2. Okay, what's the equation 2.2? I have no idea. Okay. I really have difficult thing, like equation. Okay, this works, so if I do this, there is a unique univariable Q of A. Okay, unique, establishing uniqueness. Since the equation specifies the behavior of Q of A in n inputs, this means that there cannot be two distinct polynomials at degree n minus 1 that satisfies the equation. I'm not sure, but it's like a proof thing, so I can just skip it. Specifying a polynomial via evaluation versus coefficient. Readers are likely comfortable with univariate polynomial of degree n minus 1. Yeah. This is what we're saying. Using with univariate polynomial p of degree n minus 1 that are specified by coefficient in the standard monomial basis, meaning c0 until c minus 1 such that p equals c0. Okay, this is like classic polynomial. This is the way we describe polynomial normally, and we just describe the coefficient here. As indicated before of lemma 2.3, the n evaluation p of 0, p of 1, p of can be thought of an alternate specification of p. Just as the standard coefficients uniquely specify p, so do the prescribed evaluation at the n inputs 0 until n minus 1. In fact, the equations show that n evaluation of p can themselves be interpreted, that these n evaluations of p can themselves be interpreted as coefficient for p, not over the standard monomial basis I squared ix x squared until x to the power n minus 1, but rather over the Lagrange polynomial basis delta 0, delta 1 until the delta minus 1, n minus 1. So yeah, it's hard to talk. In other words, for a set of input, for I in a set of inputs, p of I is the coefficient. P of I is the coefficient of delta I in the unique representation of P as a linear combination of Lagrange basis polynomial. Okay, I mean, I understand this, but I don't understand the point of the text. So the text is just to say we can represent our encoding either with coefficients or either with polynomials. I mean, with evaluations. A coding theoretic view. Given a vector, the polynomial Q of A in the lemma is often called univariate low degree extension of A. Okay, this is important to note. Q of A is often named, called, let's say, univariate low degree extension of A. I need to stop doing this. Sorry, guys. It's just that my mouse has like this thing where I can zoom out and zoom down, and when I take back my mouse, it does that. Sorry. The viewpoint underlying this terminology is as follows. Consider the vector low degree extension A of length p equal the order of fp, whose entry I is QA of I. If p is, I guess, larger superior than to n, then the low degree extension of A is vastly longer than A itself. But the low degree extension of A contains A as a subvector, since by design Q of I, QF of I equal AI plus 1 for a set of input. One thinks that the low degree extension is an extension of A. The LDE begins with A itself, but includes a large number of additional entries. Okay, I understand. Because this low degree extension works until n, you know, but the polynomial can still continue afterward. It's like an extension of your vector. Like, because things that are after are also like in your... Yeah, okay. It's a low degree extension. Low degree is because the degree will be n and not like p or something. And n will be largely inferior to p. So you do an extension, this polynomial will be an extension to this polynomial will be an extension of your base vector because it creates new input out of this vector. See figure 2.2. Where am I? Yeah, okay, this is the extent. Yeah, A, so you'll get 2, 1, 1. So you'll get 2, 1, 1, but the LDE will also give you 2, 4, 7, 0, 5, 2, 1, 0, 2, 1, 0, 10. Like, this is the thing, right? You get this small A that you create, and you'll get a low degree extension that like continues kind of this vector. It's like extended. Okay. Such encoding function in which the vector A is a subset of its encoding LDE of A. The vector A is a subset of encoding low degree extension A are called systematic. So it's important. Encoding functions where A is a subset of LD of A is called, I know it's not exactly the right word, systematic. I'm not using the exact word, but I don't care, it's for my own notes. And I will get back with the paper afterwards. The systematic nature of low degree extension encoding turns out to render it in a more useful in the context of interactive proof and arguments than the Reed-Solomon encoding of section 2.3. Exactly as for the Reed-Solomon code in the section 2.3, low degree extension is a distance amplified encoding of A, in the sense that for any two vectors A, B, in the vector space f prime to the power of n that differs in even a single coordinate LD of A and LD of B differs in at least the probabilistic 1 minus n minus 1 divided by p fraction of n3. This fraction is very close to 1 if p is largely superior to n. Okay. A note on terminology. In coding theory literature, A is referred to as a message, and the encoding LD of A is called the code word to the corresponding message. Okay. A message. Low degree extension of A. Code word of A, I guess. Yeah, corresponding to the message A. Many authors use the term Reed-Solomon encoding and low degree extension interchangeably. Often the distinction does not matter, as the set of code words is the same regardless. Namely, the set of all evaluation tables of polynomial of degree at most n-1 over fp. Often the distinction doesn't matter, as the set of code words is the same regardless. Namely, the set of all evaluation tables of degree at most n-1 over fp. The set of code words is the same. All that differs between the two is the correspondence between message and code words. Okay, I don't exactly understand. Whether the message is interpreted as the coefficient of the polynomial as the evaluation of the polynomial. I mean, they're just saying it doesn't matter in terms of semantics. Algorithm for evaluating Q of R. Suppose that a given vector A in the space in fp to the power of n1 wishes to evaluate the univariate low-degree extension Q of n at some input R in the field. How quickly can this be done? It turns out that O of n field addition, multiplication, and inversion are sufficient. A single field inversion is a slower operation than an addition or multiplication operation, often performed via the so-called extended Euclidean algorithm. However, there are batch inversion algorithms that can perform n field inversion with roughly 3 n field multiplication and 1 field inversion. Okay. If okay, it can be done in n time or n time. Equation 2.8 offer an expression for Q of R in terms of function, namely, okay, there are only n terms of this sum. However, evaluating the g terms require evaluating delta of j, and if it's done via its definition, this requires on field operation per term for a total of on squared. Formally, it turns out that the n values for this. Fortunately, it turns out that the n values of all delta 0 of S1 of can be evaluated just using on addition, multiplication, inversion in total. I don't exactly understand. Once these values are all computed, the right hand side can be computed. So it's like you're saying you can pre-compute this part, if I understand. Ah, no, like they're saying how to do it in on time. Okay. Here is how to evaluate it with on addition, multiplication, and inversion. First, delta 0 of R can be evaluated with. Then for each I which is not bigger than 0, you're computing it relatively to the previous result, right? Or something like this. Yeah, that's the thing. They're saying the delta of 1 can be described as S0 of R times this times this. Okay, I believe you. It's cool cool input. Let P sphere to n be a prime number given as input in the field and R in the field. There is an algorithm that performs okay, so that's the theorem they were saying. Yeah, 0 equals this, and then you can do this, and then you can do this. Okay, so there's okay, so basically they're saying, okay, that's cool, you can do it quicker. Congrats, guys. If I need to implement it one day, I will come back here, but I mean today I don't especially need the the full technical like the full experience on this. Okay, nice. Chapter 3, interactive proof. Okay, definitions and technical preliminaries. Okay, this is we're already 50 minutes in and we're starting to get started on the chapter 3. It's actually super cool. I'm like super glad. Because when we're gonna do this, I'm gonna like know so much more. How long is the chapter, by the way? I know this. I just want to know how long is the chapter. Oh, there is exercise. I don't know if we're gonna do exercise, guys. We can try. Fun. Okay, so it's 32 and we start at page 23. So it's like 9 page, which is a lot because we only done 23 page in like 3 hours or something. So that's pretty slow. That's normal. Okay, let's start by 3.1 interactive proof. Let's go quickly. Let me check one thing quickly. Before we start, I'm giving you a break of 2 minutes. Okay, let's go, guys. Let's go. So interactive proof. Given the function f mapping 0, 1 to the power of n to finite range r, a k message interactive proof system IP. Whoa. What are you talking about? You're going too quickly, my dear paper. There is a function f that maps the input 0, 1 to the power of n to finite range r. Giving this a k message interactive proof system IP for f. Okay. A k message interactive proof system for f consists of a probabilistic verifier v running in polynomial time and a pre-described honest deterministic prover algorithm. Both v and p are given the common x in this in the set 0, 1 to the power of n. And at the start of the protocol, p provides value y claimed to equal f of x. Then p and v exchange sequence of messages that are determined as follows. The IP designates one of the party, either P or V, to send the first message, M1. The party sending each message alternates, meaning that, for example, if V sends M1, then P sends M2, V sends M3, P sends M4, and so on. Okay. So we're gonna read it again afterward, just to make sure. The entire sequence of k messages T, M1, M2, MK exchanged by P and V alongside the claim answer is called a transcript. At the end of the protocol, V must output either 0 or 1, with 1 indicating that the verifier accepts the prover claim that y is equal to f of x, and 0 indicating that he rejects the claim. The value output by the verifier at the end of the protocol may depend on both the transcript T and the verifier internal randomness. Denote by out VXRP in 0, 1 the output of the verifier V on the input X when interacting with deterministic prover strategy P with V internal randomness equal to R. For any fixed value of R in V internal randomness out VXRP is a deterministic function of X, as we have restricted our attention to this deterministic prover of strategy V. Wow, this is a lot to... This is like a lot to take. So we have a function f. So first we have, like as they're saying here, the choice of the domain in this chapter is not essential but rather made by convention and for convenience. So the choice is, the domain is 0, 1 to the power of n. Meaning it's bit message by like it's just bit messages. It's of size n. I'm gonna just write it. Bit messages of size n. This is what it means. I understand this. Okay. We have a function m, a function f. We have a function f. Function f, we'd say. Function f mapping to finite range R. Maps Z1 n to R finite range, which is a finite range. A K message. Okay, interactive proof system. K message IP system. K message is the number of message, right? Yeah. I didn't understand it like this before. Messages. Okay. K-message IP system. For F consists a probabilistic. There is a probabilistic verifier algorithm V running in polytime. That's what I'm trying to, like, there is this thing. There is like an honest deterministic prover algorithm P. Both V and P are given X at the start. That's what I'm trying to understand. Like I'm reading circuit string. P provides. Let's continue to like write it, and then I will try to explain what I understand when I write. Provides Y claiming that f of x equal y. P and V exchange K messages, V needs to output if he accept the message, the claim or not. That's the idea, right? The idea is we have a verifier that runs in polyt and time. We have a prover algorithm. Both V and P are given X at the start of the protocol. So I guess you can, this is what they're saying at least. Then P provides Y, claiming that F of X equal Y. Then they exchange messages, and then after this exchange of messages, the verifier needs to say if they think the prover is lying or not. So this is the idea. So this is out VXRP, and the R is the fixed value of internal randomness for the verifier. Yeah. We just need to have R also, that, okay. Okay, so this is an interactive, that is a K-message interactive proof system. Okay. An interactive proof system, VP, is said to have completeness error delta C and soundness error delta S if the following two properties hold. Okay, this is probability. The probability that the out equal 1, yeah. They're saying that, okay. This is the probability thing. I already said I'm super bad at probability. Like, I don't have it doesn't click for me. And honestly, this is where I just trust mathematicians to know. Intuitively, for any input x, the completeness condition requires that there be a convincing proof for what is the value of fx of f in the input x. The soundness condition requires that false statement in the form fx of y for y not equal like a convincing proof. Okay, so we already know that. That is, there is no cheating prover strategy p py. No, not. How do we say this? Oh. P prime? I don't know. I don't remember how we say this, so it's okay. The cost of paramount importance in sort of T runtime and G runtime. But there are very important concepts as well. The space usage, the number of bits communicated, and the total number exchanged. If V and P exchange K messages, then K, the mean, I think it's like you round it, kind of. You round it, K divided by 2 is referred as the round complexity of the interactive proof system. The round complexity is the number of back and forth interaction between P and V. If K is odd, then the final back and forth interaction is just a back with no forth. Okay, it consists of one message to prover to the verifier, from prover to verifier. Interactive proofs were introduced in 1985 by Goldwasser, Micheli, and Rakov and Bawai. Okay. Cool. We know what an interactive proof is. An interactive proof, to summarize, it's an interactive proof system is a protocol with a prover and a verifier, where a prover claims a state and by an exchange of message is convincing a verifier that his claim is true. Okay. Argument system. It was a bit athletic to read this, but we got it. Got it, guys. Okay. An argument system for a function f is an interactive proof for f in which the soundness condition is only required to prove against prover strategy that runs in polynomial time. Okay. So the soundness is that you can make false claim. Okay, this is like interesting. Argument system is an IP system for f where the soundness as is required to hold against prover strategies that hold in poly time. Okay. The notion of soundness in definition 2.4 is called computational soundness. Computational soundness should be contrasted with the notion in soundness in definition 3.1. Okay. Which is regarded to hold even against unbounded prover that might devoid inner computational resources to try and trick V into accepting an incorrect answer. The soundness notion for definition 3.1 is referred as statistical soundness or information theoretic soundness. Okay. Okay. It's not that important to know. Like, I will remember if I need, or I will come back. Argument system were introduced by Brassard, Chaume, and Crépeau in 1986. Okay, just 1 year after. Just wondering. Who are these guys? Because they have French names, so a bit. Gilles Brassard, David Chaume, Claude Crépeau. Yeah, I'm just wondering maybe they're Canadian by the way, but like where did they study or yeah, Canadian. Exactly. Morel. Okay, interesting. Let's go back here. They have very Canadian name, by the way. They are sometimes referred as computational sound proof, but in this manuscript we will manually use the term proof to refer to statistical sound protocol. Okay. Computationally sound proof argument system. Okay. Unlike interactive proof, argument systems are able to utilize cryptographic primitives. While a super polynomial time prover may be able to break the primitive and thereby trick the verifier into accepting an incorrect answer, a polynomial time prover will be unable to break the primitive. The use of cryptography often allows argument systems to achieve desirable properties that are unattainable for interactive proof, such as reusability, ability for the verifier to use this same secret state to outsource many computation on the same input, public verifiability, etc. This property will be discussed later in survey. Okay. The use of cryptography. Okay. Okay. So, if I understand correctly, what they're saying is um, that arguments can use cryptography and are like sound computational sound proof because they are, yeah, because they use cryptography to create the proofs. So it means that you cannot you could break it if you have like super polynomial I how do they say exactly uh, super polynomial time prover, but not polynomial time prover. Robustness of definitions and the power of interaction. Okay. At first glance, it may seem that a number of aspects in definition 3.1, 3.2 are arbitrary or unmotivated. For example, why does definition 3.1 insist that the soundness and completeness error be at most 1/3 and not some smallest number? And why does the completeness condition in definition 3.1 demand that the honest prover is deterministic, and so forth? As we explained in this section, many of these choices are made for convenience or aesthetic reasons. The power of interactive proofs and arguments are largely unchanged if different choices are made in the definitions. The remarks in this section are somewhat technical and may be skipped with no loss of continuity. Okay, thank you for the fact that I will skip this. Like, honestly, I think I will. Okay, this is, I think, interesting. I guess it's this exact session, or I don't know. Let's read this, and if we think it's not worth, we'll skip it. Complexity theorists often find it convenient to study decision problems, which are function f with the range 0, 1. We think of decision problem as yes/no questions in the following manner. Any input x to f is interpreted as a question, namely, does fx equal 1? Equivalently, we can associate any decision problem f with the subset L in 0, 1, n, okay, consisting of yes instances for f. Any subset L is called language. Okay, I'm not sure I follow everything, but it's okay, it's okay. All good, guys, all good. We can associate any decision problem f with the subset L that is a subset to 0, 1, n, 0, 1 to the power of n, consisting of yes instances for f. Okay, I don't understand. Yes, okay. The formalization of interactive proof for languages slightly differ from that for function. We briefly describe this difference because celebrated results in complexity theory regarding the power of interactive proof and their variance, example IP equal p space and IP equal next p, refers to IP for languages. An interactive proof for the language L given an input x. Okay, I know. Okay, the verifier V interacts with a prover P in the same manner as the function 3.1 and accept, 0, or reject. The standard requirement for an IP for the language are completeness. For any x, there is some power strategy that can say. Let f of L taking an input and giving 0, 1 to the corresponding decision. F L of x equal 1 if x is in L, and fl equals 0 if x is not in L. Note that for x not in L, the above definition for an IP L does not require to be a convincing proof. Okay, starting to, yeah, okay. I will start to skip this a bit. I mean, I kind of understand the idea, but it's like very, abstract. The language stuff. It's very abstract. like problems and stuff like this. I think it's always been abstract to me. Maybe sometimes I will understand. I need more, like I like more and more understandable things, like less abstract stuff. I don't have mathematical background, so given a function f, an interactive proof for f. Okay. Okay, we'll only talk about interactive proof. Okay. NP and NP. NP and IP. IP be the class of all languages solved by an interactive proof system with a polynomial types verifier. Okay. Class IP can be viewed as an interactive randomized variant of the classical complexity class NP. The NP class is obtained from an IP by restricting the proof system to be non-interactive and deterministic, meaning that the completeness and seedness errors are 0. Okay, yeah, IP is like NP, but you can have errors that are defined by the completeness and soundness. We'll see soon that the IP class is in fact equal to p-space, the class of all languages solvable by algorithm using polynomial space and possibly exponential time. P-space is believed to be a vastly bigger class of problem than NP. So, this one formalization of the statement interactive proofs are far more powerful than classical. This one are far more powerful than classical static NP proofs. Because IP equals P-space, then IP are more powerful than NP proofs. Okay. It's still kind of I don't know how to explain, like abstract. That's the word. That's the word. Okay. By your powers combined, I am IP. The key to the power of interactive proof is the combination of randomness and interaction. If randomness is disallowed, equivalently, if perfect soundness equals 0, then the interaction is pointless because the prover can predict the verifier messages with certainty, and there is no reason for the verifier to send messages to the prover. In more detail, the proof system can be rendered non-interactive by demanding that the non-interactive prover sends a transcript of the interactive protocol that would cause the interactive verifier to accept. Okay. On the other hand, no interaction is allowed, but the verifier is also allowed to toss random coins and accept an incorrect proof with small probability. The resulting complex class is known as MA, short for Merlin-Arthur. This class is widely believed to be equal to NP, which, as stated above, is believed by many researchers to be a smaller class of problem IP. It's crazy that people are like working on this. It's very cool in a sense, but it's very, very abstract and a lot of theory. I think it's wow. The Schwartz-Zippel lemma. Okay, so IP equal p-space. It's just like I don't know. And you see, I don't think I will write IP equal p-space. So just doesn't make so much more sense for now. And if I need, I will come back to this exact place if it's like very important at some point. I don't believe it's gonna be super important. It's just like some definitions, and we'll be like, we're doing this because it's believed to be better and stuff like. But I understand. Okay, Schwartz-Zippel lemma. I think it's funny, but I already have notes about this, if I'm not mistaken. I don't, I guess. I don't. I literally add I have notes about. I know this stuff. I don't know where, but I read it. I think I read it in Abstract Algebra by Judson. It's definitely here. Uh, well, full text edition 2022. No, but where did honestly, I have no idea. Okay, crazy that I don't have note about this. Honestly, okay. Let's take note then. I know this stuff. Like I read it. Like I learned it at some point. Schwartz, Zippel, lemma. Okay. Let's do this. Terminology. For an m-variate polynomial g, the degree of a term g is the sum of the exponent of the variable in the term. For example, if j x1 x2 equal 7 x1 squared x2 plus 6 x2 to the power of 4, the degree of this is 3 and this is 4. The total degree of j is the maximum degree. Okay, it's 4. The lemma itself. Interactive proof frequently exploits the basic property of polynomials, which is commonly known as Schwartz-Zippel lemma. Let f be any field, and let g f to the power f to the power of m gives an m. A non-zero m-variate polynomial of total at most degree d. Then, on any finite set S, which is a subset of the field, the probability at j of x equals 0 is inferior to d divided by the length of S. Okay. Here, x, x s to the power of next x draw uniformly random from drawn uniformly at random from x at Sm and S is on the size of S. In words, if x is chosen uniformly at random from S to the power of m, then the probability that j of x equals 0 is at most d divided by the length of S. In particular, two distinct polynomials of total degree d at most d can agree on at most d divided by S fraction of points in S. Okay, I try to understand exactly. I think it's, okay, again, probability stuff, but it's like if you take a random point in Sm, if you take a product set is, okay, I think product set is not to the power, it's just that it's there is no 0 or something. No, it's not this. I don't know this notation, honestly. But if you take random x, the probability that g of x equals 0 is inferior to the maximum degree of your polynomial divided by the length of your finite set. an easy implication of the Schwarz. Okay, we will not prove this. An easy implication of the Schwarz-Simple lemma is that for any two distinct m-varied polynomial p and q of a total degree of atmos d over a field, p of x is equal to q of x for at most d times the length of the field, fraction of input. For a fraction, for this fraction of input. Okay, so this is important, but yeah, maybe that's why I didn't took note. But Schwarz-Zippel lemma says that for two, I mean, not exactly, implies, let's say implies for two polynomial p and q, the probability that p of x equal q of x is is d divided by the length of the field. So in for example, you will, if you have like two polynomials that are degree 3 and you have a field of 13, the probability that you'll get two polynomials will be something like this, 3 out of 14. That's what they're saying, at least. Okay. Oh, there's a lot of stuff to do. Let me take some water because before continuing quickly, we'll be back in 1 second. I'm back with some water. So, to continue my explanations and stuff, let's do 3.5 multilinear, low degree and multilinear extensions. 3.5 low degree and multilinear extensions. Actually, like, it does take some time to do this, but I'm actually very happy to do all of this like definition work. I think I will, like, for example, a low degree extension, I'm happy that I know what is it now. It's simple to understand now. It's like it's I had to someone had to explain it like this. The paper is very good at explaining it, I think, because I've heard of it like many times and I didn't really understood it until now. So I'm pretty glad. Let me check. Okay. So let's do low degree and multilinear extensions. Motivation and comparison to univariate Lagrange interpolation. In section 2.4, we considered any univariate function f mapping these inputs to f prime and studied the univariate low-degree extension of f. This was the unique univariate polynomial g over f prime of degree. Okay. Okay. So they're saying our input, the name was A, is actually now f, and it's a function. Like, if I understand from now what I understand, let's take quick notes. Before we had a equal a0, a1, a2, a3, an, and now it's just saying this function is called a, and if you do f a0, you'll get a1. But this is like Lagrange stuff, and this is just a function that stops, I guess, or something. The univariate low-degree extension of f. This was the unique univariate polynomial j over f prime of degree at most n minus 1, such that j of x equal fx for all x in the input. In this section, we consider multivariate function f, more specifically defined over the variate domain 0, 1 to the power of v. Note that when v equal log n, the domain has the same size of the univariate domain. Okay, I have no idea what they are talking about. Multivariate function f. So there is multivariable. There is not only f0. There is like f01, I guess, or something like this. They can take multiple things. Okay. Let's continue. Let's let it flow, and I will come back if needed. As we will see, functions defined over the domain have an extension polynomial that have much lower degree than in the univariate case. Specifically, any function f mapping 0 or 1 to the in the domain v to f has an extension polynomial that is multilinear, meaning it has a degree of at most 1 in each variable. This implies that the total degree of the polynomial is at most v, which is logarithmic in the domain size to. Okay, they are talking a lot, guys. It's okay. Let's just continue and we'll understand. Like, I need examples, basically. In contrast, univariate low-degree extension of the greater degree n-1. Multivariate polynomials with ultra-low degree in each variable turn out to be especially useful when designing interactive proof with small communication and fast verification. I can understand this, that if you have ultra-low degree polynomial, I guess multivariate ones, it's way it's way better than having one with bigger degree. Details of polynomial extension for multivariate functions. Let f be a finite field. Any finite field and f. Okay, this is. I have a problem. I don't have idea what's like. I just need the. I don't have this knowledge. What is the v-dimensional Boolean hypercube to f prime? Like, I guess it's just not that hard, but I guess an hypercube is just a cube with like more than 3 dimensions or something like this. a v-variate polynomial G over f is said to be an extension of f if G agrees with f at all Boolean valued input. Okay. Here the domain. A multivariate polynomial G is multilinear if the degree of the polynomial in each variable is at most 1. For example, the polynomial j of x1, x2, multivariate polynomial, equal x1, x2 plus 4x1 plus 3x2, but the polynomial is multilinear because the degree is at most 1. But the polynomial hx1, x2, x squared, is not. Wait a second. Sorry guys, I had to sneeze. For the survey, we'll frequently use the following fact. Okay. Okay. It's honestly a bit difficult to understand. Wait a second, I need to. Okay, I'm back. So I'm trying to understand, like, a multi-linear polynomial multilinear polynomial. No. Yeah. So it's multivariate polynomial with degree at most 1. I know this. And so they're saying that they're saying here, basically, because I feel like this notation F2, it's a bit confusing for, like, it was way clearer with the A like this, but whatever. They're saying that for all x in zero, 1, V, there is F where there is, okay. F, the MLE of the MLE, multilinear extension of F is F of X. No. Yeah. Okay. All I'm just trying, to understand what's going on. Okay, okay, okay. There is Lagrange interpolation of multilinear polynomials. So f takes this input and gives a number in the field. Honestly, this thing I don't really like it, but okay, proof I don't care. Okay, I go item. Okay, this is a good example. Ah, and we can see that there is the thing, and okay, this is great. I understand this. I understand it so well with this. Like, it makes sense. It makes sense. It makes sense. What I'm gonna do is just taking a screenshot and put it directly. But sometimes it's easier to do like this, you know. Nope, it's not the one. Okay, I will do it another way. Yeah, I don't have. I do know. That's me. Hop. This is my screenshot. It's easier to do like this. Up. And I go back here and I put this. What's going on? Something like this. Yeah, not my best screenshot, but I think it helps understanding. Whoa, I did the perfect place. Wow, fun. I think it helps understanding. You'll have multiple. Okay. Okay. Makes sense. The thing I'm a bit confused about is here. The thing I'm a bit confused about is, you have f. Like, this is already a function. So, like, for me, f is just f. But it's because if you do, like, if you already put, like, I don't know. If you find the function that maps, yeah, I don't know. It just feels like maybe I'm wrong. Okay, maybe I'm wrong actually, but for example, it's just that I don't want to read the proofs and stuff because it. Okay, the thing that I need to remember here, or we need to remember, is a multilinear polynomial as a multilinear extension that extend like this this variation to this one, and we can see that the first one here are still there, and it's just new ones that. So basically, we just take the small polynomial that we have and we extend it via multilinear extension of f, and it has a degree of 1. Important stuff. This is still a proof. Okay, this is for the time. I mean, these are important things. Like, don't get me wrong. It's just that I don't want to, like, if I need that, I will go there. But it's like very not abstract in the sense, but theoretical. Like it's much theory, and I'm more interested in actually, you know, doing the things like doing benchmark, or like the benchmarks are with code for me, not for papers. But I'm a programmer than mathematician, that's why. But for me, it makes more sense. Okay, so figure 3. Evaluating all three variate Lagrange basis polynomial at input R1, R2, R3 in the field. Okay, this is, oh, it's doing its thing. Interesting. Okay, this is the exercise. I can read them, and I'm not sure I want to do them because I will get them wrong, and that's not very cool. Database CV NVN matrix over field N. In section 2.2 we present the randomized algorithm. That's okay. Yeah. The algorithm picked a random element and output equal if x equal output equal. Suppose that instead, this is yeah, it's 3 volt, right? Suppose instead that each entry of the vector x is chosen independently and uniformly at random from F. Oh no, this is like proof 5. I don't want to prove anything, guys. It's math exercises are terrible. I just want to understand. I don't want to become a mathematician. I know that people will tell me that if I don't do exercise, I won't get it, but oh, sorry. I just don't think it's for me. It's okay to not do exercise and notebooks and stuff. It's okay. You just take what you take, and if you don't take everything, it's okay. You'll get back to the paper one day, I think. That's the way I see it, at least. In section 2.1 you described. Yeah, okay, this is the same vibe. Give her a different protocol. Okay, whoa, okay. Oh, probability, no, definitely not for me. Fix some prime p of your choosing. Write a Python program. Ah, this is for me. Write a Python program. I'm the goat of Python. Oh, I don't want to do that. Whoa. Oh. Okay. Oh, some check protocol. I know this guy. I'm working on it right here, actually. There is this thing at the time I'm doing the live that kind of challenged by a company called ZK Security, I think, not XYZ, company of David Wong, which is doing a challenge and it's using JKR, so I could do that. I'm just a bit tired right now, honestly. I think we did full we finished the second chapter, we did another one. I think it's great to stop here. Next time we'll do chapter 4. Maybe. It's quite long. It's quite a chapter, so maybe if I'm motivated I'll do everything, but IP small space. No, why do you need that? There's so much thing. JKR protocol. It's quite cool. Some check protocol, light interactive proofs. The first interactive proof cover is some check protocol. Some check. Okay, we'll do that later. I don't want to start now. I want to be super focused when I do it because it's important. So I'll stop the live here. Small live, almost 2 hours still, but still not the biggest I've done in my life. I will, as always, write the notes later about Lagrange basis polynomial, Lagrange interpolation, difference between interactive proof argument system, Schwartz triple lemma, low degree and multilinear extension, low degree extensions as well, of course. I think I've learned what I had to learn from this chapter. Even some things are a bit not super clear in my mind. I think in the end I understood like the multilinear linear linear extension, because it's just the same as a low degree extension, but yeah, it's the same thing. It's literally the same thing. So it's the same thing, but with inputs that are not in like a one-dimensional space, if I understand correctly. Not the best at linear algebra. Maybe one day I'll do some. So cheers, guys. Enjoy. Let's meet later.